In this video, we'll find the range and kernel of a linear transformation. Because we've already done examples of the null and column spaces, we'll select a different example unrelated to matrices. Let C1 be the space of continuously differentiable functions on an interval, let's say. That is, it's the set of differentiable functions whose derivatives are continuous. We claim that this is a vector space. We know that the space of functions is a vector space, so we show that C1 is a subspace of that. The constant function f of x equals 0 is differentiable, and the derivative, which is itself, is continuous. Let f and g belong to C1. We need to show that f plus g belongs to C1. Well, if f and g are differentiable, then so is f plus g. That is a basic theorem of calculus. And if f prime and g prime are continuous, because f and g are in C1, then f plus g has a continuous derivative because the sum of continuous functions is continuous. Similarly, if f is in C1, so is bf for any real number b, a scalar product of a differentiable function is certainly differentiable. And if f prime is continuous, so is a real number times f prime. And C0, the set of continuous functions, is a vector vector space. That's an example we've seen before. And we claim that the transformation from C1 to C0 that maps a function to its derivative is linear. And this comes straight from calculus. If we apply D to a sum, we're taking the derivative of that sum. The derivative of a sum certainly is the sum of the derivatives. So that's one of our linearity conditions met. And if we apply D to a constant times F, it's the derivative of that constant times F. A property we have for the derivatives is that you can pull constants out of them. And that's precisely what we needed. We will now find the kernel and range of this linear transformation. Let me jot it back down. We're looking at this linear transformation that takes a function and maps it to its derivative. The kernel of D, we're looking for functions whose derivative is the constant function 0. Certainly, every constant function has that property. The derivative of a constant function is 0. And it's a theorem of calculus 2 that only constant functions have that property. If a function isn't constant, then at some point its derivative is not 0. So these functions and only these functions. The kernel of D is the constant functions. What about the range of D? Well, the range turns out to be the codomain. It's all the continuous functions. functions. And this comes from a theorem of calculus that if f is continuous, it has an antiderivative which lives in C1, and this transformation D takes any antiderivative of f and maps it to f. So every function is in the range because every function is mapped to by its antiderivative. In this video, we saw an example where we found the kernel and the range of a linear transformation. What made the example interesting was that the linear transformation had nothing to do with matrices. It was not a linear transformation from Rn to Rm. This is what makes linear algebra such a powerful tool. Matrices and functions might seem like basically unrelated objects, but we can use the same tools to study them both.